Okay, so we just talked about ALOA and the need for ALOA to have this random backoff time in when a collision is detected. And collision is detected when an acknowledgement is not arriving before the timeout in the ALOA protocol. Now, so how should we choose the maximum backoff time? So remember that TBA, or rather the backoff time, TB, is a random variable which is uniformly distributed between 0 and TB max. Okay. So what happens when TB max increases? Okay. Well, if we make TB max very large, say, now suppose we make it 2 years. Okay, what happens with the probability of repeated collision then? As we increase TB max to some very, very large number, what happens with the probability of, we have a collision here, what is the probability that the next transmission that we collide, what happens when we make TB max large?
Decreases?
Yeah, it decreases, right? So, I mean, if we make this silly large, then we can get this probability down to 0. So why don't we make this silly large? Well, because it's silly, of course, but what else happens if we make TB max long?
Well, I don't remember the name for it, but it will take a long time as well to establish a connection.
Not quite, but think of this, that the time from here to here, in this case, is the frame delay, right? So this is the time it takes for the frame to be delivered. So delays increases. Nobody likes delays, okay? So we want to make TB max large enough to avoid collisions, but we want to make it small enough to not introduce unnecessary delays, okay? And to complicate things here is that what is a good value of TB max? Well, in this case, we only had two active transmitters, or we only had 3 active transmitters here. But suppose we have 5 active transmitters, then, so when we have 2 active transmitters involved in a collision, then we don't need to make TB max too large in order to avoid collision again. But if we have many nodes, say 10 nodes, trying to access the channel at the same time and collides, then we need a longer TB max. Okay. So in a way, the maximum delay backoff time we choose, we should choose that proportional to the number of transmitters involved in the collision. But this we typically don't know. Okay. But there is one way in order to somehow adapt the maximum backoff time, and that is to count that for each new repeated collision we increase TB max. So we start with the low TB max and hope for the best, and then if we get repeated collisions we keep on increasing TB max from retransmission to retransmission attempt. So this is the idea of a strategy called binary exponential backoff. Okay, so what is it? It's a method to adjust the maximum backoff time to the current load. Okay, so it's very dynamic. So it doesn't work like this, that we know that there are 20 Wi-Fi nodes attached to an access point. It doesn't work like that. It works on what is the current number of transmitters that are accessing the channel. Okay, so that's what we would like to adjust TB max to. And the idea is the following. At retransmission attempt k, then we randomly choose an integer in an interval from 0 to 2 to the power of k minus 1. And then we set the backoff time. This is wrong. It should be here. It should be TB max. Okay, so the maximum, It's right, sorry. So then we choose the backoff time to be r, a random variable, which is this integer, times t slot, where t slot is chosen different in different protocols. It could be a propagation time or a slot time or something like this, or a duration of a packet. It doesn't matter for this discussion really. But anyways, we see that TB max, which is the highest number that R can take on, which is 2 to the power of k times t slot. This is the maximum delay we can have in the backoff. It approximately doubles for each new retransmission. And so it goes something like this. So if this is the backoff window between 0 and 2 to the power of k minus 1, okay, then so this is the, we select R to be uniform in 0 to 2 power of k minus 1. And TB, the backoff time, is R times t slot. Okay, so we see that TB max depends on the maximum TB can be is when R takes on its maximum value, which is 2 to the power k minus 1. So if we then look at this backoff window, how it increases as we increases k, when it's the first attempt, then it's very small. Okay, so it's, we basically don't have any backoff time. But at the second attempt, we between 0 and 1. At the third one, it's between 0 and 3. At the fourth one, it's 0 to 7, 0 to 15, 0 to 31, 0 to 63, and 0 to 127. So you see this exponential growth in this, the maximum backoff time. So very quickly, we go from a small backoff times to very large backoff times. And the rationale behind this is that if we have many repeated collisions, that probably means that we have many users trying to access the channel, and therefore we need a longer backoff time. Okay, so going back to the protocol here, what we do is that if a station has a frame to transmit, it puts k equals to 0, and then it sends its frame, and then it waits for a timeout. And then if an acknowledgement has been arriving during the timeout, then everything is okay. Then we don't have to do anything. If there is no ACK received within the timeout, then we have detected a collision. And then we increase k. And if k is greater than k max, then we stop. We give up. Otherwise, we choose R within, we choose R, and we choose that between 0, 1, up to 2 to the power of k minus 1 in this interval. And then we wait TB, and TB is R times t slot. And then we go back here, and then we try to send the frame again, wait for a timeout. If there is still a collision, then we go on and we wait probably longer as we go around here. Now, so we wait a random time, so we cannot say that we always wait longer, but our chances to wait longer increases. So the TB, as we go around this circle, has a tendency to increase. Okay, so this is called binary exponential backoff. Questions? No, okay. All right, so let's now try to analyze this ALOA protocol and see is it any good. And to do that, we need to introduce a little bit of mathematics here, not a whole lot, but a little bit. And what we need to do now is to model how frames arrive to the MAC layers in the stations which are attached to the medium. And to do that, we usually, the simplest model, which is used very often, is called Poisson data traffic. So how does that work? Well, it deals with Poisson random variables. Perhaps you've seen these variables before. If not, then it's not terribly complicated. But anyways, we use these Poisson random variables to model a number, namely the number of independent events that occur during a certain time period. Okay, so that's usually when we use Poisson random variables. It could be, for instance, the number of requests for a certain document at the web server, or it could be the number of frames transmission requests during a certain time. Okay, and we will use the latter here. And the probability mass function, okay, so it's a number, so it's a discrete random variable. So we have a probability mass function, and it has one parameter. You know, the Gaussian random variables, which is continuous, they have the mean and the variance. And once we know that, we know the PDF of it. Here we only have one parameter, and that's known as the rate or intensity lambda. Okay, which is the average number of events for this time period that we have decided to do. So if y is distributed according to a Poisson with intensity lambda, so this is the notation. Y is the random variable. This tilde here is distributed as p for Poisson and lambda for the intensity. That means that the probability that y takes on an integer k is lambda to the power of k over k factorial e to the negative lambda. And this is for k equals 0, 1, and so forth. And it's 0 otherwise. And it's not very difficult to show that the expected value of y is lambda. Okay, so lambda is the average number of events that happen during a time period. And then it is the probability for different number of events is given by this formula here. So, I mean, if we had one of these processes would look something like this. We have some time intervals, and then there are a certain number of events here. And suppose that lambda is about 3. That means that on the average, there are 3 events happening here. But there is no guarantee it's be 3. It might be just 1. And the next time is like 5. And then it's like 2, and so forth, right? So during each time period, we get another realization of this Poisson random variable. But on the average, we get 3 in each time slots. But sometimes we get 1, sometimes we get 0, sometimes we get 10. But on the average, 3. Okay. Now, if we have 2 of these Poisson random variables, say z and y, and they're independent, then we would have another process with another intensity, say 2 here, and then maybe we get just 1 event and perhaps 3 events here. So it's a little bit less events when lambda is lower, a little bit more when lambda is higher. When we add these together, we get a new process where the intensity is the sum of the 2 intensities. It sort of makes sense, right? So if we count the number of total events here, we get 2 here, we get 5 here, we get 2 plus 3, we get 5 here. So the intensity increases. Okay. So Poisson has this nice additive feature that the sum of 2 independent Poisson random variables is also a Poisson random variable and has an intensity which is the sum of the intensities. That's one of the nice properties here, and that's why it's so heavily used in theoretical calculations. Okay, so oops, what happened? Okay, nothing happened here, but it happened here. Okay, any questions on Poisson? No. Okay, so let's continue that. So let's do a very simplified law analysis here. So the analysis is actually a little bit flawed, so it's not rigorous, but it gives the right result. So sometimes it's like that. And it sort of makes also intuitive sense. So with a little bit of a grain of salt, we can accept this analysis and then use the main result, which actually is true if one makes a more accurate analysis. Okay, so the assumptions is the following, is that all frames have the same transmission time or duration, TF seconds. And during TF seconds, what happens then? So we think of this basic interval here as TF now. Under TF, seconds, there is a number of new frames that arrives, which is generated for transmission. That's a Poisson random variable, which has intensity lambda n for new. The number of old frames scheduled for retransmissions is also a random variable, z, which has another intensity lambda r. And we think of y and z as being independent. So w, which is the sum of y and z, is a Poisson random variable with the intensity g, where g is the sum of the new frame intensity and the retransmission frame intensity. Okay. So w is the number of frames which are generated per time slot for transmission. Some of them are old frames, retransmission frames, and some of them are new. So in a block diagram, we have new frames arriving to the system, and these are the sum of all frames from all stations, right? Then we also have back-off frames, frames which have been transmitted previously, but have collided with somebody else, and we have put them into back-off, but the back-off timer has expired, so they also need to be transmitted during this time slot. So all of these W frames, a number of frames will be transmitted. So W here is a Poisson random variable, and then it goes over the channel. Now, if W happens to be such that there are no collisions here, then that frame would actually go through. But if W is such that we have a collision, then all of these would go back into back-off, and then eventually needs to be transmitted again. Okay. So think of it like this, that we are a number of stations, and we get frames from above that we need to transmit. Okay. So when I transmit this, two things can happen. Either it goes through, and I get an acknowledgement back, or I don't get an acknowledgement. If I don't get an acknowledgement, I go into back-off, which means that eventually I need to transmit this frame again. And I keep on doing that until I get the frame through. But at the same time, my neighbor might get new frame that he or she needs to transmit, and so forth. Right? So we have new frames coming from the layers above, and we have frames which are in back-off. And all of these needs to share the same channel. Okay. Then we also make the assumption that propagation delay is 0 or negligible. And we also assume that we have infinitely many stations, which means that the frame rate from each station is very small. So this new frame rate doesn't change when users are blocked. So these are all details why this analysis is a little bit flawed. But let's go and view the main result here. So if we have Aloha, okay, now, so what is the probability that the frame goes through? That's what we're interested in. So suppose we are interested in knowing the fate of this blue frame, which we transmit. It has a duration which is TF. Okay. So this is the reference frame. And we would like to calculate what is the probability, if we transmit this, that it will go through. Okay. And we will say that it goes through if it's not colliding with some other frame. So at the same time as we transmit this frame, there is a probability that there are other frames being transmitted. Right? Because Aloha doesn't do anything. As soon as we have a frame to transmit, we transmit. So in this case, there is a collision from the purple one and a collision from this, what should we call it, peach-colored frame here. So here is a collision for the blue frame, and then it will not go through. Okay. So we have the reference frame and the interfering frames. So how to analyze this? What is the probability that the blue frame is not colliding with some other frame? That's what we're trying to aim at here. So the number of frames which are generated during these, which is known as the vulnerable time here. Okay, so let's spend some time here. Vulnerable time, what does that mean? Well, it means that if a packet from some other station is generated at any point in time during this vulnerable time, it will collide with the blue frame. Okay, so I'll take that again. So we have a time period here. Any frame, any interfering frame which is generated during this vulnerable time will collide with the blue frame. Partially or fully, but it will collide, right? So this purple frame, which was generated at this point in time, and the other frame which is generated here. Both of these will interfere with the blue frame and will cause the blue frame to not go through. All right. How many frames are generated here? Well, it's a Poisson process, and the intensity is that we, on the average, have G frames being generated in the first period, TF seconds, and G frames in the second period here. So in total, during the vulnerable time here, we have a Poisson number of interfering frames with intensity 2G. 2G. And the 2 here comes from the fact that we are looking at the time 2TF. If we only looked at TF, it would be G frames on the average. If we look at 2TF, it will on the average be 2G frames being generated. Okay. So a particular frame is successful if exactly 0 other frames are generated during this vulnerable time period. And this would then happen with probability e to the negative g. This will happen with the probability e to the negative 2g. Okay. Remember that the intensity of this Poisson random variable is 2g, and if we go back to look at the probability that Poisson random variable is equal to 0 is lambda to 0, which is 1, divided by 0 factorial, which is 0. So when k is equal to 0, this is equal to 1, and we just simply have e to the negative of the intensity. Okay, and the intensity here was 2g, so the probability of 0 interfering frames is e to the power of minus 2g. Hopefully you follow this. It was a little bit quick perhaps. Okay, so now we know the probability that there will be 0 interfering frames, and therefore what is the probability? Then we know that the probability for this to go through is e to the negative 2g. Okay. Now, how often do we transmit frames here? Well, these are generated according to a Poisson random variable with the intensity g. So in each time slot, we generate g of these reference frames on the average. So the throughput is then rho or equal to s. S is rho and s is the same thing here. S is just chosen here because it's the variable that was in the original paper for this. So S is G times the probability of no collision, which is G times the probability of 0 interfering frames, which is G to e to the negative 2G frames per that we get through per frame duration. Okay, so a little bit quick perhaps, but if you look at this at home, you would I don't think it would be super difficult to follow this. This is the throughput, and we will see plots of this in a second. So how can we improve on this scheme? Well, one thing one can do is to, instead of allowing frames to be transmitted whenever they are ready, we slot this. Okay, so frames can only be transmitted during certain time slots. And this is known as a slotted ALOA. So in slotted ALOA, we have a time slot time, which is equal to the duration of a frame plus some guard interval. And then frames can only start to be transmitted at the beginning of slot times. So this green frame can be transmitted here, but not at any other time. And B can start to transmit its frame here, say, and C can start to transmit its frame here. So we have, at the beginning of a slot, we can transmit frames. That's the only time where when we're allowed to transmit frames. And then we see that the green frame here, if it started to be transmitted here, it will arrive at C at this point in time, which is equal to the propagation delay between A and C. And as long as we increase the slot time to be a slot duration plus a guard interval, which is greater than the propagation time, then we see that the green frame here will always be contained in the slot. It can never go into the next slot. And the same thing, the blue frame here can never creep into the adjacent slot. So by having these slotted times, and we can say that frames can only be started at the slot boundaries, we confine frames to be inside one slot. Okay. If we have it like this, then for a slotted ALOA, we have a reference frame here, and then interfering frames that would cause interference here are frames which are transmitted at the same slot boundary. So with the same assumptions as for unslotted ALOA, and with guard intervals which are negligible compared to the frame duration, so the slot time is equal to the frame duration, then the vulnerable time is TF in this case. Okay, so this is the vulnerable time now. It's TF seconds, while for unslotted, it was 2TF. Okay, so that's the difference now. Okay, so what is now the throughput? Well, the throughput is still G times the probability of no collision and G times the probability of zero interfering frames. And we see now that we have G to the power of negative G. And that's because we have 1 TF here. Okay. So if we take this, we have G times E to the negative 1 times G. And this 1 is because we have 1 TF as our vulnerable time. Remember, it was 2 for the unslotted ALOA. Okay, so that's where this factor of 1 or 2 comes from. Okay, so let's draw some plots and see how the throughput for ALOA and slotted ALOA varies. Okay, so we have here an expression for the throughput for slotted ALOA, which is S equal G times E to the power negative G. And for ALOA, it's the same, but it's with exponent negative 2G. And then it just follows this as we vary G. So here we have S as a function of G. So we're interested in maximizing throughput. Or we're interested in here calculating what is the best throughput we can hope for when we use ALOA and slotted ALOA. And that is to find the peak of these things. And we see then for ALOA, the peak arrives when G is equal to 1/2, which means that this is the maximum throughput for ALOA. 0.18. Okay, so about 20%. So during each frame duration time, TF seconds, on the average we get through 0.2 packets. What is the best we can hope for? Well, it's to get through 1 packet. So the efficiency of this protocol is about 20%. 20% of the slots are successful. Okay. If we go to slotted ALOA, we increase this to be about 0.37. So 35% of the slots are successful. So these are not, it's not great efficiency numbers, but the protocol is also very simple. So the question is, of course, if we can do better, and we can. But these are the simplest thing we can ask for. So if we're content with the simplest, which is ALOA, then the best we can hope for is 20% efficiency, or that, yeah. And if we go to slotted, then we get about 37% probability. So why should we ever use ALOA when we can have slotted ALOA? Any suggestions? Yes?
Perhaps it's easier to implement.
It's definitely easier to implement. We don't need synchronization to figure out the time slots. That's one reason, a big reason. And the second reason, which is actually not visible in this analysis, is that we have now assumed that the guard interval is 0. And the guard interval is not 0. It has to be greater than the propagation delay. So when the guard interval increases, which it does when the propagation delay increases, then the efficiency for slotted ALOA decreases also, because we have to, have these guard intervals, which means that we cannot use the channel during that time. So two things here. So if we have a very large propagation delay, then slotted ALOA is not any good. Like the actual efficiency of that would decrease. Okay. But anyway, so both of these are used in practice, slotted and unslotted ALOA. Can we do better? Well, we can definitely do better. And the most obvious thing to do is simply to, instead of transmitting blindly, we listen first to the channel, and if it's busy, we don't transmit. Because if it's busy, we know for sure that we will mess up that transmission by transmitting ourselves. So let's be a little bit polite and listen to the medium before we actually start to transmit. And this is the general idea about the family of MAC schemes called carrier sense multiple access. So it's a listen before talk. So listen before the channel when you have a frame ready. If the channel is sensed as idle, then transmit, possibly after some initial delay. We will see that in some detail protocol later. If the channel is sensed as busy, then we don't transmit. Rather, we wait until the channel becomes available, idle, or we back off a little bit and then try again. So if A here listens to a channel and declares that the channel is idle here and starts to transmit its frame, there is still a possibility that there will be a collision on this channel, and it will be happening if B and C gets a frame which is ready during their vulnerable periods. And the vulnerable period is the time when during which from the time where a frame has started to be transmitted until it's detectable at the other side of the medium. So if you remember back to our toy example here, this was equal to the propagation delay. So we can still have collisions even if we have carrier sense. That's what I'm trying to say here. So we need to protect ourselves against this. Okay, so there are a number of variations of carrier sense multiple access, listen before talk, and that is basically how we, what we do when we sense the channel to be busy, or what we do if we have detected a collision. So there are three main ones: persistent, non-persistent, and p-persistent CSMA. And let's see how these work. Basically, it's like this. If we have one persistent CSMA, if I have a frame which is ready for transmission, I listen to the channel. If the channel is busy, I keep on listening to the channel until it becomes available, which happens at this point in time, and then I transmit. So this is a very aggressive protocol. So if I have a frame to transmit, I listen to the channel. If it's busy, I wait until it becomes available, and then at that very time instance I see that the channel becomes available, I immediately transmit. Okay. So very aggressive. Okay. The opposite is to use something which is non-persistent, which basically does the following. It's a very polite protocol that if we sense the channel to be busy, then we back off for a random time, and then we sense the channel again. If the channel is busy, then we repeat the whole thing. So we back off, and after the back off, we sense the channel. If the channel is idle, then we transmit. Okay. So this is a more polite protocol. It's not as aggressive as one persistent. And then there is a compromise between these two things, which is called p-persistent. What it does is that it senses the channel until it becomes idle, and then it transmits, but not with a probability, only with a certain probability. So it transmits with probability p at this time. Otherwise, if it's not transmitting, it waits until time slot has expired, and then sends the channel again. If the channel is busy, we go into back off, and then after back off, we sense the channel again. If it's idle, then with probability p, we transmit here. But with probability 1 minus p, we try again after a time slot. If the channel is available here, we transmit with probability p, and perhaps we wait another time slot, but eventually, after an idle time slot, we transmit. But we don't transmit with 100% probability. Okay. Here we transmit with 100% probability, and here we transmit with 100% probability, but after a back-off time. Okay. So any questions on this general rules here? I know it goes a little bit quick now, but it's actually easier if we look at the state diagrams here to figure out what's going on. So in one persistent, we sense the channel. If the channel is busy, then we go back and we sense the channel. If it's busy, we go back and sense the channel. So we go around in this loop until the channel is idle, and then we transmit. So that's the easiest one. The non-persistent is that if the channel is busy, then we wait a random time, and then we measure the channel again. If it's busy, then we wait another random time, and so forth. If the channel is not busy, then we transmit. P-persistent, which is the more complicated one, works like this. If we measure the channel, and if it's busy, then we go back and we do this, which is almost like what we do in one persistent. But once the channel becomes idle, we don't immediately transmit. We draw a random number from 0 to 1. If that random number is less than p, then we transmit. Okay? But there is a probability that we don't transmit. If so, we wait a slot and then measure the channel. If the channel is idle, then we go. If the channel is busy, then we go back here and generate a new random variable, r, and if it's less than p, we transmit. If it's greater than p, then we go back and wait another slot. If the channel is busy, then we go into back off instead. So these are the three main methods. Okay, so I will skip that. But anyways, just to finish off here. We have talked about ALOA, transmit directly. Okay, we have talked about slotted one, where we only transmit at slot boundaries. To improve performance, we can use carry sense multiple access, listen to the channel before transmitting. And the idea is that if the channel is busy, there is simply no rationale to transmit, because then we for sure will mess up that ongoing transmission. There is no need to do that. The problem is that we cannot avoid collisions because we still have a vulnerable period even if we do carry sensing. and then we need to handle the situation where we need to decide what to do if the channel is busy. And then we have these three different methods, main methods. Okay, so we'll talk more about this when we meet next time, which is on Monday. So have a good weekend.